here. Now in chapter 4, where we'll deal with the famous halting problem, like I say, one of the pillars of the theory of computation. I won't say what it is, because we still need more theory to understand what's going on with the halting problem. But in that chapter, so we'll develop techniques that you can prove some languages are undecidable. Undecidable. In other words, you cannot decide whether the language is, well, the strings in that language can be accepted or rejected. I assume that's what it means. Okay, given the wording here. Anyways, maybe hang judgment somewhat until you finish chapter 4, the next chapter, and then I suggest come back to this, and you'll probably see this in a clearer light. One of my criticisms of Sipser as I go through is his lack of clarity. I think he could have worded things in a clearer fashion. All right, like this, for example. Is that something that's supposed to be really obvious, or is it something that will only become clear with greater knowledge? Stuff like that. Not happy. All right. Now change topic somewhat. Now we begin a block of work. We'll go through 4 examples of the use of Turing machines to, well, in fact, decide on a language. We'll show how the Turing machine is able to detect whether a set of strings, in other words a language, whether it can accept each string in that language. And this machine will halt, it will accept or reject, and therefore it's a decider. It's a Turing machine that halts. Okay, and the 4 tasks, the 4 languages, the 4 Turing machines that we will design and describe in reasonable detail. We'll show how the Turing machine does its job, how it works on a given language. And we'll have 4 languages and 4 machines to illustrate how Turing machines work, because we haven't really done even one yet in detail, just sort of quite high level overviews so far. All right. Now you could, now we did it before with finite automata and PDAs, you could give a formal description, right? You write out in detail the k-tuple, for finite automata a 5-tuple, for PDAs a 6-tuple, and now for Turing machines a 7-tuple. And you write out in detail, a description of all its parts. Now, of course, the hardest part is the transition function, as always, the delta. Now, for a Turing machine, that's where all the work lies. I mean, it's just, it's tedious, it's cumbersome. So in practice, that's what it's sort of saying here, that tends not to be done, like a full description, because there's just so many details involved. And except, for tiny examples of Turing machines, maybe then you do it completely. But for the most part, mostly, you use a kind of higher level description that does not go into every little detail, but it goes into enough detail. So it's a compromise. It goes into enough detail to give you a pretty good overview of how it works, and enough detail that you can understand how it works. And if you really wanted to know the finest level of detail, you could. Okay. So in practice, what that means is that you are not given the full transition table. But of these 4 examples we'll do, the transition table will be given, but it's sort of like an extra, and it's not explained in the text. It's up to you if you like. You could ignore it, and just use the higher level description that is given for all 4 cases. Or if you really want to go into the nitty-gritty, I mean really the nitty-gritty, the fine level, the fine print like in a contract, you can. You're given the option. For the first 2 of the 4 cases, you are given the transition table, the state diagram. State diagram. Or state transition diagram. Okay, so you with little circles for all the states, and the transition arrows labelled, suitably labelled, for all the possible transitions between 2 states, right? And it's complete. So that's a complete, the state table, the state transition diagram gives you complete details. It's all there. You can extract everything you want from that. You can create the formal description of a machine from its state diagram, state transition diagram. Okay. Well, that's pretty well what I've just said. Well, maybe I can elaborate a little bit here with the high-level description. It's a compromise between a full formal definition and a sort of more hand-wavy approach. It's usually, it's precise enough so that you understand what's going on, okay? And B, it's much easier to understand instead of being drowned in a wealth of details, as you would be in a fairly complex state diagram. Right? Your state diagram, God, it looks like a state diagram in a biochemical molecular chain reaction type chart. I don't know if you've seen these charts where you have like the states would correspond to proteins, and then you have the arrow, the transition arrow from one protein to the next, and you'd have the label on that transition arrow would be the enzyme, the chemical, the biological catalyst, speeds up the reaction. So the label is the name of the catalyst, usually something ASE, and the final state is just the next protein, the catalyst or the enzyme. A catalyst, an enzyme is a biological catalyst, which itself is a protein usually. So you're using proteins to help make proteins, right? And they're complex. Oh, it's just a tangle. It's like a cobweb. It's just a maze. Well, that's what a state diagram can look like for Turing machine as well. Just this mass of. It looks like spaghetti. Okay. Right. So the higher level description is usually much easier, right, to understand. And don't forget that these higher level descriptions are really just shorthand. They're just shorthand for the full formal description that would include the state diagram, state transition diagram, right? Okay, well, I'll stop there. Ciao.